Welcome everybody to the first CRP Meccanica and VELO3D live webinar. Pleased to have you here. My name is Marco Fornari. I am the Sales Director and Quote Manager in CRP Meccanica. I am joined today by my colleague, Jon Porter. He is the European Business Development Director. So let's get started. Support-free is the future of metal AM. Couldn't be more true. So a few words on CRP Meccanica. We are based in Italy. The motor valley of Italy is Modena. And we have extensive experience in serving the motorsport world. And all of our clients are heavily invested in the motorsport sector, and so have we for the last 50 years. So we have extensive experience in very complex components. We are the exclusive distributor for Italy and the account distributor for Europe of VELO3D machines. CRP Meccanica will also be providing throughout Europe sales and after sales support, service and maintenance, as well as production backup when customers may need more firepower, should we say. Then we can be contacted to help you build the components that are most requested at the time. So a quick brief on CRP Meccanica. We have 50 years total of experience in rapid manufacturing, CNC manufacturing, as well as prototype casting and sintering for casting. We have 20 years experience in the metal additive field, and we are recently obtaining the ISO 9100 aerospace certification. We are already ISO 9001 certified. So our history in the metal additive field begins in 1998 with this lovely gearbox that you see here, and completely made out of titanium cast with the sintered lost wax molds that we helped co-design with our clients. We had the molds prepared, sintered, and then sent for casting in the United States. So we've been in the game of sintering and additive for quite a while. The mentality is there. And that's why we decided to partner specifically with VELO3D, because they are one of the most cutting edge partners in the metal additive world today, as we had been back in 1998 when we produced the very first titanium, basically 3D printed transmission gearbox case. As I said, many of our customers are in the motorsport field. You will recognize some devices here, and we've been basically pushed throughout the years in more and more complex parts. As I like to say, we've been forged in pain because the requirements of these customers are extremely high, both timeliness and precision and performance. A quick overview of our internal capabilities. We were born as primarily a machining company, where today we have a total of 16 5-axis milling machine of the best brands. We have 3 CNC live tool lathes, 2 conventional lathes, 3 EDM wire and sinker machines to complement all the other machining operations. We also have an in-house certified titanium welder, and we have as many as 4 active inert welding chambers where we can weld titanium, which is notoriously very difficult to do. We employ the best software in the industry with Hypermill and GibbsCam and Cimatron Elite for our CAM softwares, and Autodesk Inventor and CATIA version 5 for our CAD programs. And here it is. We decided to partner with VELO3D, which is a relatively young company, but absolute leader in its field, for their revolutionary support-free technology, which will be the buzzword throughout the presentation because they deserve it. And we will be discussing their capabilities and what they can do for you. This is a slide that I've been released to show to the world because it's been made formal and official now. VELO3D has supplied Spacex as much as 22 of their machines within the last 3 years. So this is the #1 customer that they have, and everybody knows who Spacex is and what they do. The engine that you see in front of you is the revolutionary Raptor engine that is used on many cutting edge of their boosters that employs heavily additive components made by VELO3D. So everybody understands the reliability and the critical parts that are involved in rocket engines like these. And the choice of VELO3D, I guess, speaks a lot to their performance. Another happy customer is Honeywell, which is in the process of qualifying VELO3D's machines for the use in aerospace components. Qualification of these machines is usually very stringent, very tedious, and the fact that Honeywell is pursuing it speaks to the high degree of quality and confidence that they have in this supportless technology. Many other happy customers in this splash screen you will recognize from the space, aviation, defense, energy, and OEM. Many of these are already employing VELO3D's technology, and some of these are researching into it, and the list is growing daily. I've literally had 2 new contacts just today from big firms that we haven't been able to add to the screen yet. And no compromises on design. This is the point of this presentation mainly, meaning that with the help of CRP Meccanica, we can help our customers understand this new breakthrough in technology and understand that they are no longer limited by the compromises of the obsolete and current additive machines, but now they can release their designs far more than they ever have before. There may be some coaching still left to do overall to understanding this technology. But now with VELO3D, you can finally afford to make shapes and geometries that were before forbidden to do. And we have a manufacturing network which is live today, mostly based in the United States, to which we have access to. So we can quickly direct all your requests to the appropriate manufacturer with the appropriate materials, with the appropriate machine, of the several machines that we will illustrate shortly.
Thank you, Marco. Yeah, thanks, Marco. Let me just move on to the next slide, and let me take a high-level view of what laser-powered bed fusion is. I think we're all familiar with the phrase 3D printing, and it's essentially...
Sorry.
Thank you. It's essentially the production of a three-dimensional component through a series of two-dimensional slices, and this is typically managed in a manufacturing process where there is a piston inside a chamber, typically in our case a round chamber, and that powder inside that chamber is powder, and that powder is laid down through a recoating process, and typically we work in the VELO machine at 50 micron layer thickness. And each layer is then melted in the strategic position of the two-dimensional section you're trying to create using a laser. And in the case of our machine, we have 1 kilowatt laser capacity, and we have 2 lasers in our machine working simultaneously. So once that laser has melted that new layer, the process then repeats. So the piston steps down, another wipe of powder is put across, and the next two-dimensional section is fused and welded to the previous layers lying below inside the machine. I'm about to show you a video now, and just before we go to that slide, I just wanted to explain a little bit about it. There's 2 items in the video. The first is showing the manufacturing of a reasonably large, complex component, and it'll stitch together a whole series of photographic images to demonstrate to you how quite a large part is built vertically, and all you're seeing is the outline of the wall thickness, because as Marco's mentioned several times, we're able to build parts like the one shown in the video without any supports, and you can see as the part is generated, there's no supports present. Second part of the video is really quite cool as well. This is showing our ability to build parts within the AM system, within the VELO system, that are unsupported or not in any way coupled to the build surface or the build plate. So these parts are built free form and standing within the powder, and it allows you to build these parts in layers and subsequent layers on top of one another. And again, it's a unique attribute of the VELO process. So if we could just take a look at the video, that would be great. So 2 1 kilowatt lasers performing the initial build sections on the part I was trying to describe. And you'll see now we'll move into looking at this part being built through a whole series of those 2-dimensional sections. And there is no support. All we are building is the part. We're not building any supports within the process. Second part that I mentioned, which I think is absolutely fantastic. And this is free-floating parts within the build. So a high-pressure gas turbine blade, unrestrained, unsupported, just supported essentially by the metal powder that sits around it. So a unique attribute of the VELO process. So supports, we've already mentioned them a number of times, and I guess it's worth explaining a little bit about why they're needed. The process is essentially a whole process of rapid expansion and contraction of metals. We're using a laser to melt parts, small sections of the powder very, very quickly, and that presents a whole range of internal stresses which can manifest themselves inside the part. So we have a desired outcome. We have a little archway that we'd like to reduce, and if those internal stresses are allowed to manifest themselves inside the part, invariably they will come into conflict with each other. And the outcome, without any supports in place, is that the part will fail, and the part will deform in the way that's shown in the central image there. So the way that most parts need to be manufactured through additive manufacturing is to put in place supports, or as we perhaps could also refer to them as anchors. These are the little items shown on the image on the right, the red stripes. And these are about anchoring the component down and making sure that it remains stable during the manufacturing process. And these supports have to be added ultimately as part of the post-processing technologies and techniques. You'll have to spend time to remove those. So this is really where we start to stand out. Again, shown in red. You'll see a component like this, which is a shrouded impeller, which is from one of our customers. It's a reasonably large component. And conventionally, this part would have to be supported. Now, there's a range of supports you can see there. And you could argue that the supports underneath the component are reasonably easy to get to. So once the part has been produced, you may want to argue that those supports are reasonably easy to remove. And that's fairly true. But you can also see that there are supports inside the flow channels. And those in particular are extraordinarily difficult to remove. And not only when you're removing them are you finding it time intensive and labor intensive, is that you're offending, essentially, you're damaging a critical flow surface. So there is it's an undesired outcome in the production of parts just like this. Looking on the right, this quite simply is the alternative solution that we provide. So you can see, genuinely, we would produce that part without any supports in place. There's a small external support on the very outer diameter, but that would typically be post-machined away as part of the final machining process. And this is a sort of process that could be applied at CRP. This is their bread and butter business of producing high tolerance parts. So how do we do it? Well, we work with CAD data. We don't, our software doesn't accept STL files, which are the normal within this industry. And we need step files or CAD data because we need to interact with that data. We need to apply a series of steps within our own flow software. So we have a product called Flow. And what it does is it looks at the component on a feature by feature basis. And what it does is it applies one of up to about 25 different build profile recipes that we have. So if it sees a vertical wall or a low angle wall, we have a recipe for that. And the flow software will apply it. And as the part is being built, that recipe is in place to build that part without supports, or that feature without supports. But as the part evolves and, for example, goes from a vertical wall into more of a bulk section, then the recipe will change again. And what we're typically able to do then is to fully exercise the 1 kilowatt capability of our lasers and speed up the manufacturing process because we're just laying down bulk volumes of material in the final part. And this part you see here, you'll see it again later in the presentation, but it's important to point out the part you see is as made, so that hasn't received any post-processing whatsoever. So the quality of the surfaces we're producing, I think you'll agree, is outstanding. So we present ourselves and we present our business, and we refer to it as a full stack. And what I mean by that is that we not only provide the printer, we provide the supporting software around it. So it's important for you to realize, as I've already mentioned, that we need the CAD model, and that would be interpreted by our flow software. So what we're essentially doing is prescribing the build process, and that's what the software does. That prescribed outcome is executed and manufactured inside our metal printer, the Sapphire printer, which is shown there. Allied to the manufacturing process are a whole series of sensors inside the machine. So just over 900 sensors are currently on board. That includes the onboard metrology for the machine to self-calibrate before each and every build. But those calibrated sensors are then used to derive volumes and volumes of important information for you to validate the parts that you've built. So we have a second piece of software called Assure. And what that does is it centralizes all of that key manufacturing data into a single point and provides a validation of the build. It proves to your customer that the part you produced today is the same as the part you produced yesterday, and consequently is the same as the part you produce tomorrow. So we have a standard Sapphire machine, which was shown in the previous slide, that has a build volume, which is shown there. We have a round build plate, which is slightly unusual, and it's 315 millimeters in diameter and typically working to 400 millimeters in the Z direction. Now, what we've also done as well is we've taken the goodness from our original machine and stretched it out. So we also have the same diameter build plate, but working at a 1 meter in the Z direction. Now, this has been particularly useful for some of our customers, particularly in the oil and gas industry, but it provides a reasonably unique working space for very long, large components that are very typical of some of the key sectors we're now supplying into. If we could just take a look at the next slide, that's great. But more exciting than that in some respects is the future product. We're always excited about what's coming next. And that is the Sapphire XC, and XC stands for extra capacity. It's a much larger machine. So physically it's obviously larger because it has a much increased or greatly increased build space internally. We now have a build plate. It's remaining round, but it's 600 millimeters in diameter now. And in the Z direction, we can manufacture parts up to 550 millimeters. Now, what we've had to do here as well is we've had to increase the number of other things, and primarily we've also increased the number of lasers. So we now have 8 kilowatt lasers in this machine, and the machine, and they improve the productivity no end of the machine. In early trials, it appears that we're getting at least an increased throughput of at least 4 times that of the standard machine.
Yeah, that is absolutely amazing. I very much look forward to this XC being released, I believe, third quarter of this year.
It's coming. It's probably maybe fourth quarter this year into early part of next year, and the interest in the machine has been outstanding. We've received a number of reservations and pre-orders for the machine. I can't go into exact numbers, but it's extraordinarily exciting and very we're very happy with what's going on.
Yeah, I can't wait to go see it with my own eyes in California as soon as it's possible. That'll be really an outstanding machine, which takes us to a machine is only as good as the products that you can make with them. And a good product needs to be of good quality. How do you track that quality? So far, many of the additive systems have relied on outsourcing processes just like X-ray inspection. Well, VELO3D software package, as Jon mentioned, has this package called Assure. The Assure quality control system is an all well-rounded quality control suite that does several things. One is checks the health status of your machines. So the screen that you see here is called tool health. By tool, they mean the machines that you have installed in your shop floor. Here you can monitor the build progress of every machine, the health of every sensor, every critical sensor of that machine. It also instantly warns you when you need to swap out any filters, and it has hot swapping capabilities, whether something is fallen out of alignment, and I mean by that lasers. And if anything is basically running slowly out of spec, because it can warn you that it's creeping towards a possible problem, and it can send you emails and alerts and notifying the technicians to react. So this is one part of it. As John mentioned, there are over 900 sensors. I'm told 970 sensors in this machine that are being tracked, recorded, and graphed for the most part, which is shown here in the sensor data. So if you are a bit of a control freak, a machine like this is fantastic for you, because you can definitely go look, go understand, and explore what is happening in real time to your machine. For example, here it's talking about peak height and recirculation filter, and literally there's dozens of screens like this. By peak height, what do I mean? Which brings me to the best part, in my opinion, of this software. This is the height mapping part of it. And then we will go back to the full build report that Assure actually is able to generate for you. So every part can receive a build report, which is fantastic. So back to the height mapper. The height mapper is a special sensor developed in-house by VELO3D that is able to record in XYZ the powder bed within an accuracy of a few microns, as little as 1 micron in the Z and 5 microns XY. This is an amazing feature that I don't believe anybody else in the market has, a 3D scanning feature of your powder bed. What it does is takes a regular camera image and a 3D relief map of your powder as it's being laid, after it's being laid, and after it's being lasered. What this shows you is the amount of deviation from normal that you have occurred, that happened. What you see in blue is the material densifying and solidifying. So it's losing a few microns in thickness, but this is perfectly nominal. And what you see here in this slide in red and yellow are parts of the build that have come up. As John mentioned, the laser sintering technology, let's say, has usually suffered from parts curling up. And that's why you need so many supports tying everything down. Well, with VELO3D, now you can not only be much more aggressive with your 3D prints without supports, but also you can check the health of your part as it's growing. Every single layer is recorded, and as it's being recorded, a 3D model of the imperfections that may lay inside of your part are being mapped. At the end, when you want to create your report for that part, you may go and check out the various predicted porosities that have happened in that part to further adjust your model or your processes for the next part. So this is an incredibly powerful technology. This is the kind of things that build confidence in the customers that are maybe a bit on the edge on adopting additive technologies. With a quality suite like Assure, this gives great confidence to designers on the design side, but quality managers in the quality department office, because it gives you, as I said, as a control freak, it gives you great understanding of what has happened in your part as it was growing, so you may change it and better it next time. This is truly outstanding. Materials. Well, all the classic, most high-performance materials are offered today. So obviously grade 5 titanium, Inconel 718. This is aluminum F357, also known as A356. It's basically an LC7 alloy. Hastalloy X, which is a nickel-based super alloy. And then coming soon, the famed Inconel 625, for which I received a request today, and Scalmalloy, for which I received a request yesterday. So I really hope that Velo releases these two materials, because I have customers literally asking for it as we speak, basically. The material developments are not finished here, because with the purchase of a system, VELO3D, within a minimum of 3 months, will develop material of your choice within these major categories. So say, for example, you're interested in absolutely high performance parts in titanium 6246 or 6242, which is a high temperature titanium alloy. VELO3D may develop it for you free with the purchase of the system, of course. Material properties, obviously this is always asked, how dense are these parts? Well, they are usually guaranteed within 99.9% of the volume. So basically fully dense, and better than casting, that's for sure. Geometric accuracy is roughly guaranteed in 0.2% for any linear dimensions, but this varies on application, especially depending on the aspect ratio of your component. But this is something that is a bit tricky to quantify with just one number. So again, to the quality control and certification, I love this quote, because it speaks to the importance of keeping track of how your part grows. And this is especially true in high performance fields like aerospace. So the largest latent risk in the utilization of laser powder bed fusion parts in critical spaceflight application lies in the limitations to verify individual part integrity. Verify individual part integrity. This is exactly what the Assure system does. It can verify and show you with its report at the end the part integrity of your part before you send it off for weeks and weeks out to get X-rayed or to do NDT at a third-party company, and so on and so forth. This is truly an amazing feature that I believe nobody has today. Which brings us to applications.
Great, thanks, Marco. Let's just talk a little bit about additive manufacturing, because over the recent years it's been often made promises it maybe can't always cash the check on. We often talk about design freedom and the opportunity to create essentially what we want, but it's not entirely true. We'll often find we have a desire, but the reality of the additive process, along with other manufacturing processes, is that there are still some constraints. So we often talk as well about design for additive manufacturing, or DFAM. And essentially what that really means is there are some concessions. So we need to understand, even when using additive manufacturing, that there typically have been some compromises that need to be made. And actually one of my colleagues summed it up rather nicely in an earlier presentation I saw. He used to be a manufacturing engineer, and he used to be in, as he said, he used to be in the business of making design engineers cry, because he would often have to have a conversation where the design couldn't be met by the manufacturing process. But really, we need to sort of think about how we go forward. So until now, that's been the case. But right now, we need to consider using Velo to skip that step. So if we look at the next part, it's a heat exchanger. Fairly typical of the industry, I understand that. We're not unique in our ability to make these, but we have had huge success. We can build very, very conformal parts with our machine. This is a customer that we have down in Australia. And with all the inherent properties of the materials and the ability to flow liquids through parts with very low pressure loss, you create parts with really exciting performance improvements. Fine features is something that we're very good at as well, to have leak-proof walls inside a component like this, typically down to about 320 millimeters, but that's typically constrained by the material. So it's aluminium in this case, but we have some pluses and minuses on the leak-type walls that we can produce based on the material that we're manufacturing with. And it's fair to say there's a little bit of honesty here in some respects. I'm showing in the background there a part with some supports. Look, if they're easy to remove and they provide more guarantee of build success, then that's fine. That's fine, because there are still forces in this process that need to be managed. We can do it in a number of ways, and one of them still is to use some supports. If they are easily removed, then why not? the turbine part that I showed a little bit earlier on, just to give some validation, and just to quantify some of the improvements we made. So we worked this project with a company called Sierra Turbines in the US. And these are the sort of improvements that these guys were seeing. So not only were they consolidating, it was 61 parts into this single item, and you can see there's a mesh section, there's a lattice section at the bottom there. There's horizontal surfaces, vertical walls with holes straight through them, and it's allowed us to produce a part for those guys that is 10% more power dense. And more importantly, in terms of the service life of the component, it has a much higher degree of durability by 40 times. So it's a massive series of successes and wins for a company like this. And it really starts to open up the ability to build in a much more unconstrained way using this fantastic technology. This is a more recent piece of work that we've done. Now, this is for some supercritical CO2, and this is about the transfer of heat into electrical energy. It's a little bit conceptual in my mind, but it's a fantastic area for us to be working into. It doesn't look a particularly sophisticated part. If you look at the image on the right, I understand that it's massive. It's highly structured in some of its wall thicknesses, and when we build parts like that, we can really exercise the 1 kilowatt laser capacity that we have. We can really bulk through these very heavy sections. But it's important for you to realize that there are some very, very fine volute sections down at the bottom. So I can see Marco sort of circling around them. So it's in the central part there. Now, conventionally, these little volute forms, which is where the supercritical CO2 is transferred in and around the turbine that sits internally here, these would not be produced or not be able to be produced conventionally using a regular additive machine, because those supports are critical to forming those features, but are just unremovable. So we don't have the opportunity to do that. But if you look at the solution that we provided and the part that we've built, and is now in full test, and we've got separate seminars that you can dive into on YouTube to see this. That volute section is completely support-free, and it's critical to the function of this part. And this is fundamental to the success of this new piece of technology, which is all driven by the new energy sector that we're having to actively develop very, very quickly to manage the way forward. So taking a look at the next slide. We've already seen images here as well of the part that now being made for Honeywell. A large shrouded impeller. We've accelerated the development time, so time compression is something we always talk about in additive manufacturing. This is pertinent here. And typically they had a design that they just really wanted to continue to make. The volumes were right, but they didn't have to do any critical redesign of the component to make it successful through our process. And that's quite interesting as well. So we're able to do with a Velo machine a lot more direct part replacement than I've ever seen before in my experience within this industry. Typically, to use additive, you tend to have to design immediately for it to make it successful from an economic point of view and from a performance point of view. But there are also opportunities using Velo to do direct part replacement. So if you have very low production runs, very low annual quantities, there's an opportunity for us to build those parts for you. Another new part, a perfect marriage in some respects. This is part of KW Micropower, so another gas microturbine business. And this is really, really quite an interesting part. It fits as part of the exhaust section of the product that they make. Now this gets particularly hot, and when it gets hot, the magnets that are embedded in the system start to deteriorate in terms of their overall performance and power. So what this part really needed was a cooling jacket. And what we have been able to do is we've been able to design and build this part with that cooling jacket in place. Again, if you were building this conventionally, that cooling jacket would need to have some amount of support in there for it to go and complete the manufacturing process. But the Velo solution is not to have any of those supports. So that cooling jacket is fully formed and is allowed to flow. Now, the interesting part here is that what we use to cool this component down is the fuel that's going in at the other end of the microturbine. So the irony here is that we're pumping fuel around this cooling jacket. The component itself is being reduced dramatically in temperature from about 170 degrees C down to room temperature. And at the same time, the fuel is being warmed. So the fuel is being primed for use. And that is a true benefit to the combustion cycle of the process of the product. So it's a perfect marriage in that respect. We have a part which is now cool. Magnets inside now perform at the required amount. The fuel that's required at the other end of the same device is now preheated and warmed and is more readily to burn. an exceptional piece of work. I've been in this industry for a number of years, and I never thought I'd be able to talk about a part like this. A fully contained, in this case, a fully contained fuel vessel is pressurized, and you can see the images left and right there, and you can get an impression of scale there with the image on the right. But to build an unsupported dome like that, this stands alone. Only the Velo system is able to do this. So we have these critical recipes, these critical build parameter sets that allow us to build through into a perfect horizontal position. So we have an opportunity here again to move the technology and this manufacturing process into the manufacture of parts that truly cannot be made by additive manufacturing, if that makes sense. So we often talk to our customers about the components that give them the most pain and the most heartache, or even with their original knowledge on additive, there will always be parts that will sit outside their ability. And that's where we fit in. We take additive to a very much a different level. And again, we're reducing weight, we're turning around the time it takes to process these parts is plus, plus, plus. A really interesting part as well. This was also done for KW Micropower. This is a 250mm round diameter part. This was the first part we helped them develop, and this has led to the subsequent business that I've already mentioned in one of the previous slides. Titanium part, large diameter, and the opportunity working with Velo is to build a part like this flat down inside our machine. We don't have a heated build plate, and this part was sort of moved around the industry for various companies to consider and to quote against, and it was just a no-quote item. And we were able to produce it. So you can see again, you can see the blue highlights on the left-hand side there. This has through channels which helically run from the internal diameter to the outer diameter. These are all fully formed without any supports inside. Fantastic part. And again, some post-processing required there, but just typically machining. So some drilling and tapping, and a little bit of turning on the ID there. But I'm sure that's something that Marco and his team could support you on if you had a part similar to this.
Easy peasy.
Brilliant. Let's take a look at that. So a lot of unique capabilities. We're very happy to consider designing without limitations now. It's often been promised with this industry, with additive manufacturing, and I'm working with Velo now as I see this. I believe there's much more to be true right now. We can help you produce performance parts quickly, effortlessly. And we can make those parts for you, and we can make sure that they're valid and make sure that the parts are exactly what you require. So we can validate the part. The genesis of our machine is from the semiconductor industry, and that's quite interesting. So we've applied a lot of techniques that are used for making hardware in the semiconductor industry in the way that we've manufactured our machine. So if you can appreciate a business that in the semiconductors, where they are typically building slice by slice, layer by layer, when they're producing silicon wafers, the adaptation of that philosophy and that sort of way of working has come all the way through into our product. And it allows the machine just to have that high sense of capability and that high sense of repeatability. And all of that provides you with assured quality, a much faster deployment, increased reduction in time in the overall development cycle. And more importantly, is that the post-processing time is dramatically reduced. If you don't have supports to remove, then you are moving into a space where your additive process is starting to produce a product. It's not just producing a part, it's actually producing something that's far, far closer to the finished product.
Do you need the special powders? Are the powders similar to conventional SLM? Do you have material data?
I can answer that one. No, we don't need special powders. And the powders are indeed identical to the reference there of SLM. So we use the same particle size distribution, so typically 15 to 45 micron. So it's conventional in every way. We are, as a business though, we are powder agnostic. So we don't sell powder, but we're very interested, as Marco mentioned earlier on, we're very interested in supporting you developing the right recipes for the powder that you would choose to use on your machine. So we have the ability to do that. And of course, we do have some material spec sheets because we cannot build our machine without using powder of some sort. And we have technical data sheets available if that's, I believe they're on our website, so they're available there.
It's very interesting, the assurance system. Does it have a closed loop principle in order to correct any defects in progress?
So,
well, interesting. It used to. maybe 2 or 3 years ago, the Velo machine was able to run in full closed loop. So we were able to manufacture under those conditions. But the reality is that is not appropriate for nearly all of our customers. Our customers are typically working in very highly regulated spaces. And regardless of the machine being able to identify changes and adapting to them, they are more interested as the manufacturers to manufacture parts the same way each and every time. So I guess that you can argue that they accept a degree of failure in some respects, but what is most important to them is to be able to build the part in exactly the same way each and every time. And we do that because the build file that we create using our Flow software, I hadn't mentioned before, but it's truly transferable. So what I've witnessed using the Velo product is that once the build file is created, it can be used on any Velo machine anywhere in the world, large or small. So it can be on our XC or on our standard Sapphire machine. And it's a critical success that we've also engineered. So it means that the build file is truly transferable. And to that end, what we're currently looking at doing is developing MMPDS data for the AM process using the Velo machine. And we're able to use a single build file on multiple machines at multiple locations and get the same results every time. And we're just in the final stages of proving that now. And I think that's a unique asset that I hadn't mentioned until now, but it's a fantastic opportunity for this process to become truly industrialized.
It is not completely clear whether the support-free result depends only on some software recipes or there are also some technical features implemented in your machines.
Yeah, there's some proprietary elements to the success of the support-free, but principally it is through the development of the recipes that we have. So if we have low incidence angles or through holes, then we've developed a recipe. And I guess it's the same. We have, these are like little routines. Maybe Marco will concur, but in the CNC process, you will have a routine for producing a hole and a routine for producing a thread, or a routine for just a flat milling. It's the same. It's in some ways it's the same approach. We just on a feature by feature basis have these recipes which allow the geometries to succeed, and it's proved extremely powerful tool.
Yes, I think there's also another component apart from the software side. With the VELO3D machine, we have a hardware side that takes care of building, let's call it the impossible, which is building without supports. The hardware side is a contactless recorder.
I thought you weren't going to mention that.
Right, because it's a twofold sort of recipe. Software that handles very low overhangs with a high amount of precision and dedicated recipes, and then hardware that implements it. Without the hardware, you can't do what the software is dictating. Without the software, the hardware couldn't do it. And so this contactless recorder system is able to never push on the part that lays inside the powders. This is part of the secret sauce, basically. You're never pushing on the part, you're never touching it, it's contactless, and this is something absolutely unique to the VELO3D systems.
Classically, the supports serve to support the workpiece and also to cool it. How do you ensure this second function?
Cooling. Well, it's still completely surrounded by powder, but more importantly, since you aptly mentioned, they can be used for cooling. Well, you can also manage cooling from the other side of things, your laser power and your laser routine. So if you don't overwhelm your melt pool in that location with your laser spot size and power and focus, you can actually control heat without the use of supports.
What is the minimum size features you can achieve?
Okay, we don't normally sort of talk about our sort of our laser spot size in a great deal of detail, but typically I've seen minimum feature size of around about 150 micron, but it's typically dependent on the material that you're processing. But around 150 microns is something I think we're able to achieve. But if the performance of that feature is, for example, if it needs to be leak tight, against liquids or something like that, then there'd be some challenges there. But if it was just a physical, for example, if it was a turbulator inside a heat exchanger, then we'd probably be into that kind of region with some of the materials that we manufacture in.
What NDT methods could you use on the parts you produce?
Well, it's not uncommon for customers to manufacture test coupons. I think Marco mentioned that earlier. So I guess you're looking at CT scanning, dye penetrant. So non-destructive testing, isn't it, NDT?
Correct, non-destructive testing. So CT scans, ultrasound testing, as well as liquid dye penetrant, magnetic inspection with particle magnetic inspection. Basically anything that you've been using conventionally in the conventional machining world, you can use on additive parts with the same processes, basically. So no restrictions.
Could you please clarify the file formats for the data?
So native CAD files are what we want. So anything from Siemens NX, SolidWorks, anything step files are perfect for the. So, but anything that's a direct CAD output from your CAD software. Our software cannot work with STL. We need to be able to understand the data in terms of the features that are in the part, not just as an STL derivative of the original CAD data. So we need to be able to go into all of the features for the flow software to work.
Is there a difference in surface finish based on the orientation of the surface in the powder bed, rougher down skin, for example?
Yeah, typically on a vertical wall, on a side wall, if I was to use a sort of an SA scale, you're looking at around sort of about a sort of a 4, 5, 6, 7. But on some of the inclined faces, you're probably more into sort of about 12 to 15 SA.
Yes, and I can add to that on the downskin processes, especially the lower the angle of your part, the more incidence of rougher surface you may get. But with the assured quality software, since it is tracking the melt pool and it is recording the height with the height mapper of the part as it's being printed, it can predict where the roughest areas will appear. So yes, they will be a little bit rougher, but you can tell exactly where, and maybe next time avoid it or go pinpoint exactly where it is, go fix it post-processing.
So it says a very interesting presentation, surely looks like a great improvement on the technology. Does the absence of supports affect in any way the capability for nesting several parts within the same powder bed? Potentially, provided that the parts are afterwards extractable, they could be stacked very close together.
Here I'm holding in my hand the perfect example that we just saw in the video earlier in the presentation. This is one of those turbine blades that were grown without supports and in perfect 3D nesting. There is a requirement. The requirement for perfect 3D nesting without supports is that you may begin printing the part from a point. So this blade was printed as you see. It was grown from this point up. You may not choose to print it like this, where an entire edge, a very long edge, would be the first thing that appears to be printed. But if you can start from a point, depending on your geometry, of course, and make it grow as such, then you can successfully 3D nest without supports.
And build in layers. So you can build subsequent parts in layers above.
That's immense productivity that's unmatched by anyone else in the industry. But yes, geometry dependent, but absolutely.
Great.
Okay. So potentially all the materials that can be used in a PBF process can be produced support-free.
Yep, the materials that we mentioned in the presentation, absolutely, yeah, we would be doing ourselves an injustice if we did it any other way.
So again, thank you everyone for joining us today. We will be having more of these sessions as we progress and expand. And for any and all inquiries, please do contact us at info@crp-group.com or at the Italian phone number that you see here. We speak Italian, French, and English. So feel free to contact us, and hopefully see you soon. Thank you, everybody.
Thanks very much.
Thank you, John.